Cristina Cifuentes from Oracle is going to be talking to us about secure programming languages. Thank you. Over to you, Cristina.
Thank you. So, for the past 12 years, myself and my team have been working on a lot of static analysis techniques and dynamic analysis techniques. We've been focusing initially in languages like C, C++, then Java, then PLSQL, and JavaScript, and many other languages. And the thing that we've come to realize is that regardless of language, a lot of the vulnerabilities are the same. So it seems that as new languages get developed, we keep on having the same type of vulnerabilities happening over and over again. And so that led me to start looking into various different programming languages and try and understand what language, what security abstractions are being provided in the languages, and why is it that we have so many vulnerabilities. So the work that I'm going to present today is really focusing on a data-driven approach, and we're driven by data in order to have a definition for what a secure programming language is. Now, before I give you my talk, our slide from Oracle, just to say that this is research, and it may never be a product, as any research may end up being, and also that anything that I say is my opinions, and it doesn't necessarily reflect the views of Oracle. Okay. So when we started like this summer school, we were all talking about fun facts. And so here I give you a little bit more fun facts. I'm based in Australia, and as such, I have like a different world map view. And what you can see here is Australia in the middle of the world, and a lot of my work, tends to be like going backwards and forwards to the US, right? And in my academic career, I was actually a lecturer initially. So when I graduated from the Queensland University of Technology, I went to the University of Tasmania, then I went to the University of Queensland. I ended up going on sabbatical leave to Sun Microsystems, to the research lab, ended up staying, didn't go back to academia, and then when I went back to Australia, I was still with Sun. Later, Oracle acquired us, and that's where my group is based. So we're part of Oracle Labs in Australia. And when I was at Sun, my manager was Mario. So there it is. And we were 11,000 kilometers away, and it's really cool to have a manager that is so far away. They let you do whatever you want. So what I'm going to talk about today is what is a secure programming language, and I'm going to give you a quick introduction at the end of the session as to what is the technology that we're going to use for tomorrow's session, that is going to be a hands-on session to really try and start thinking about some of these secure abstraction ideas, okay? And so this talk on what is a secure programming language, there's a paper that Gavin Bierman and myself have written, so you can have like the full details if you actually search for that paper, okay? Now, as I mentioned, we're taking a data-driven approach to try and understand like what would make a language a secure programming language. And we've taken the data from the National Vulnerability Database. And this vulnerability database collects all of the CVEs, so all of the reported vulnerabilities of exploits that have happened against those vulnerabilities, right? And these are unique exploits. And the same exploit may happen against like various different pieces of software, so you only see like one entry, one CVE per exploit, okay? And when you look at the compounded data for 5 past recent years from 2013 to 2017, what you find is that there are 5,899 exploited buffer overflow vulnerabilities over those 5 years. That equates to 3.2 new buffer overflows per day being exploited, which is a significant number, right? And then when you look further into what is the top 2 type of entry in this National Vulnerability Database over those 5 years, you find that injection vulnerabilities are actually very close also to buffer overflows. 5,851 unique exploited vulnerabilities. So this equates to the order of 3.2 new injection vulnerabilities being exploited every day. And you have to bear in mind that this data doesn't have all of the vulnerabilities in the world, of course, right? These are the ones that get reported. And then when you look at number 4 in this data set, you find that information leak has risen up to 3,106 exploited vulnerabilities. So that equates to 1.7 new exploited issues on a day-by-day basis, right? And if you look at those 3 different areas, what you realize is that 53% of all of the exploited vulnerabilities that are reported in that national vulnerability database relate to these 3 areas, 53%. So that's more than half, right? And when you start thinking about it deeper, you go, actually, these 3 different areas are really in the realm of programming language design. Why is it that we have so many of these issues? It's not like our developers want to write incorrect code on purpose, right? It's because the programming languages are not supporting them in order to write vulnerability-prone, vulnerability-free type of code, right? And it's a little bit depressing, actually, to look at when did we start knowing about these vulnerabilities, right? You have things like buffer overflows have been exploited since 1988, maybe even before some of you were born, right? So this has been known like forever. Cross-site scriptings have been around since the 1990s, and you have SQL injection fully explained in the literature since 1998. And why is it that we have so many of these issues today, right? So what I'm going to do is first go through a few examples of vulnerabilities in these 3 different areas. And this is just really to ensure that everyone understands what are the type of vulnerabilities that we're talking about. Some of you would already know them. But in any case, let's go through all of them, okay? Buffer errors, like the first category of issues. All of these examples, I'm quoting them from the Maitre website because they explain each of the different vulnerabilities. They have a category called CWE, Common Weakness Enumeration, where they explain each one of them, right? And for buffer errors, you have different type of buffer errors that can happen. In this particular case, you can see that we have some code. We have like a host name here that is an array of 64 characters. So this is being stored on the stack, right? And in this particular code, we have a stack-based buffer overflow. Like, anyone can spot it? Right, yes, so the string copy down here, right? So we have our 64 character array. There's no check as to what we're copying into it. So this other string may be larger than 64 and no check was done. So we may overflow, right? So that's the issue there. Now, smaller piece of code, very similar type of issue, but this one is happening on the heap, right? We have a buffer, but that buffer is going to be allocated dynamically through malloc. And then we're also doing the string copy in this case. And notice, like, this one is very trivial because we're doing it against argv1. So same type of thing, you can have a buffer overflow in that case. Now let's look at a different type of issue, cross-site scripting. Cross-site scripting is one of the most common type of injection attacks that you can find. And in this piece of JSP code, we have a reflected cross-site scripting issue. What we're doing in the code here at the top is just, we have a request, HTTP request, we're getting a parameter, let's say for an employee ID, right? And then later in the code, we're just going to go and print that employee ID. And anyone familiar with cross-site scripting type of attacks? Go ahead.
Yeah, so it depends on where the parameter comes from, but I suspect that I could send a URL to someone with this these EID parameters set to angle brackets, script, blah, blah, blah. Just read the session or read a cookie or something.
Correct, yeah. But in this employee ID here, we're not actually doing any type of checks, so we could have anything at all, right? And then when we're rendering, the browser is going to execute like whatever is in that particular string, and it could be anything, right? Like we could be executing some JavaScript code, for example, or anything else, right? We could be redirecting you to another website, things like that. So there's a cross-site scripting there. Now, we have another example of a cross-site scripting issue here, and in this case is a stored cross-site scripting, so a little bit different to the earlier one. We have longer code, we also have a connection, we're creating a statement, we're going to execute a query, right? Select start from employee, where ID equals employee ID, and then we're going to check what is being returned. If it's not null, then we're actually going to display the name of that particular employee, right? So that gets displayed down here. So what could be the error in this case? Right, yeah. So in this case, the issue has to do with the actual name that was stored, right? That if this name was stored in such a way that it was not sanitized, checked, then when we retrieve it, we're just going to display that string, and effectively, if that string contains something bad, well, we're just going to go ahead and display it, right? And let's look at another type of injection type of issue. Oh, sorry.
If you go back one slide, so
this one.
I mean, I get this issue, but also the second line with the construction of the select statement looks highly suspicious. I mean,
correct.
The idea is, but still, this is like, it looks very, very dangerous out there too.
Correct. Yes, yes, it does, which is like this one, yeah. SQL injection. Yeah. So with this SQL injection, right, like we're getting a username. We're going to have a query where we're going to make use of that username. So assume we're getting like an authenticated username in this particular case, right? There's a query, select star from items, where the owner is the authenticated username, and the item ID equals some text from that item name, right? And then we're going to go and execute this, right? So the issue here, I think several of you have already kind of like inferred what it is, right? With SQL injections, when we're using strings for SQL queries, then we need to be very careful with those parameters, right? In this case, we have an authenticated username, so that's not the issue. But what do we have here in terms of the text for the item name? And again, if that item name contained data that had like back quotes, then we could actually be dropping the whole table, right? Or we could be doing other types of things. Exactly, it's the little Bob's table, drop student type of example, right? And last example, information leak. So this is like the third type of category that I talked about. With information leak, in this particular case, let's see, we have a location for a client, right? And we're connecting to that location. We're setting the location for a particular current user. And then later in the code, there may be an exception. If that exception happens, what we're doing is that we're going to actually display like an error. This app has experienced an error. And further, we're going to dump a log. And you can see here in the log, we're just dumping information about the code exception. So what is the error in this particular case? Right? So with information leak, it all depends on what type of data you're actually making available. And a very common type of mistake is that in logs, we start making available information that shouldn't be made available to other people, right? For example, in this particular case, we're going to dump all of the information about the user, including like the location data for that particular user. And this may be something that shouldn't be displayed like normally. If you have also like personal identifiable information, it would be the same thing, right? You shouldn't be dumping that information for anyone to read, right? So that is one example of information leak. Right?
But I don't get it, because in the third line we're somehow doing something with the location to the local variable called current user, and then we print something about user capitalized, which is a different thing. So it's not obvious to me that we print the location of the user.
But we also just use the exception, which could also contain information that we don't want to leak.
Correct, yeah. It's how much information you actually have in that exception, how much you're making available, right, on this one. And the thing with logs is that they're made available to a lot of people, not just to like a few individuals that should get access to that type of data. Okay? So these are just for illustrative purposes, just so that you have an idea of the type of vulnerabilities that we're talking about. Now, when we talk about mainstream languages, what we're doing is that we're taking again data as the way of determining what are the mainstream languages. And you can have various different ways of determining what is a mainstream language. What we did is that we took the TIOBE index, and from the TIOBE index, we looked at the data of the past 10 years, which ones have been the languages that are most commonly used according to the TIOBE index. You could use any other index, right? And I'm pretty sure that you would get very similar type of results, right? So based on like the TIOBE index over the past 10 years, the most mainstream languages have been Java, C++, Python, C#, PHP, JavaScript, and Ruby, right? And a lot of these vulnerabilities that we're seeing that are being exploited are happening in, of course, mainstream languages, right? And when you look at those mainstream languages and you start mapping them against those three different categories of vulnerabilities, which I've drawn here in terms of a Venn diagram, what you realize is that only some languages provide us support for not having buffer errors whatsoever in the language, right? Java, C#, and JavaScript fall in that category. There are few languages that have actually looked at how to avoid injection type of vulnerabilities. And you have the Ruby language, you have the PHP language, and version 1.1 of the JavaScript language also had this issue.
Question, what do you mean by non-injections in this slide? Because for instance, PHP has removed all inclusion, which is really easy to do.
Right. Here I've included like languages that have had a concept of some form of injections, right? Because none of these are full or complete, right? Yeah. And then for information leak, like none of the mainstream languages actually have like the right support. Yeah.
Index considering the main frameworks of those languages, for instance, for example, Ruby, I think most of the web apps for Ruby are built with Rails, and Rails has its own vulnerabilities, but some of them have been fixed throughout the time. So do you have anything to say?
Right, so the way that the data is stored in the National Vulnerability Database, there's no easy way to differentiate like which ones came from frameworks as opposed to the language itself, right? So yeah, so that data is not there, unfortunately. Okay, and then the most interesting thing to highlight here is not only that there's like no abstractions that have actually made it to mainstream languages in the area of information leak support, but more widely that there's no language here in the middle, right? Like there's no one language that we can point to and say this mainstream language has actually looked at abstractions for these three very common type of vulnerabilities that happen in today's world, right? So our definition for secure language is such that we're taking into account these three different classes of vulnerabilities, right? So whichever vulnerabilities are the common ones today. Top three, 50% of all of the issues that are being exploited worldwide. And what we're arguing is that a secure language ought to provide first-class support for avoiding these type of issues. Because if the language had that support, then developers wouldn't have to create code that is very hard for them to actually get right, okay? And it would make it so much easier, so much better for innovation, and then everyone could focus on other type of issues that may emerge. So throughout the code and the talk, what I'm going to do is to make use of these two different abstractions. Performance overhead for any type of abstraction, secure abstraction that you're considering. And this is because, of course, like the performance of your compiled code is important. And when you end up with solutions that take too long, performance-wise, then people don't tend to use them that often, or they only use them in certain restricted domains, right? Now, the other abstraction that I'm going to use is cognitive load, because cognitive load has an impact on what the developer can actually understand. If you have an abstraction that works really, really well, but not many people can understand it, they're not going to use it, right? Or they're going to use it only in certain domains, right? And so clearly, like out of this diagram, what you can see is that the ideal abstraction would be down here, right? Something that performs really well, that has like almost no cognitive load, and that's really hard. And the non-ideal abstraction is the one that is up here, right? And we'll go through the three different categories, and we'll just categorize examples of some of the security abstractions that have been seen in different mainstream languages, and also other potential abstractions that could make it mainstream. Right? So let's look into buffer overflows. So with buffer overflow, the unsafe abstraction that we're all used to is the fact that we as developers have to do manual management of pointers in languages like C and C++, right? And why is that high cognitive load? It's high cognitive load because to get it right, it actually is hard to do it, right? It's very easy to write pointer manipulation and get it wrong, which is what we're seeing in the vulnerabilities that are being exploited. Why are there so many? Right? After more than 30 years of knowing about these issues. So that's the unsafe abstraction. And in terms of safe abstractions, I give you like two different examples, and we'll talk about these ones. You have managed memory, right? Which is an example of a low cognitive load type of abstraction. You as a developer don't need to worry about, like, how do I manage memory? The runtime system is doing it for you. Right? That's like the perfect example of a low cognitive load type of abstraction. You don't even have to think about it in most cases, right? And in terms of performance, it does come at a certain performance overhead. For some applications, that performance overhead is not an issue, and so many languages implement managed memory these days. For other domains, like the systems programming domain, they still consider like there's some overhead in this type of solution, and so they prefer other solutions. So the other one that we're going to talk about is lifetimes and ownerships in Rust, right? Which is a newer way of looking at the problem, which, you know, has low performance overhead, but it does come at a certain cognitive load, right? So very briefly, to avoid buffer overflows dynamically, a lot of languages these days, right, a lot, are using managed memory, right? And with managed memory is a concept that was first introduced in 1958 in the Lisp language. It's now being used widely in a lot of different languages. And this abstraction, the fact that your runtime has a garbage collector and it keeps track for you as to what memory needs to be deallocated and how it needs to deal with memory, it's superb for all developers, and that's why it's so popular, of course, right? Low cognitive load. And it works really well in today's processors for most of the applications, right? Now, I want to focus more on one of the abstractions that you guys would be less familiar with, and this is the Rust abstraction. How to avoid buffer errors statically. Okay? And what Rust has done is that they've provided guarantees in terms of memory safety through making changes to the type system. And in their type system, they have the concept of ownership. That is a concept that was used, that comes from C++, and we'll have an example on that coming up. And they also have this concept on borrowing. And what's interesting with the concept of borrowing is the fact that when you have your pointers, you can have a shared borrow, right? So I can share a pointer, but when I share this pointer, you cannot mutate it, okay? Or I can have a mutable borrow, and if I have a mutable borrow, then it cannot be aliased. And what that prevents is a lot of the type of errors that you see in languages like C and C++. So when you talk to developers about, like systems level developers, about some of their hardest vulnerabilities that they found, you know, something happened in production, they went back, and weeks later they really determined what the issue was, and it was because of some pointer that was aliasing somewhere that they were not aware of. You know, this is what Rust is preventing through this concept of borrowing, because you cannot do this at the same time, and the type system is checking it for you. So let us look very briefly at some examples, right? So with ownership, with resource acquisition is initialization. In Rust, you can have resources can only have one owner, right? And when you look at this code here, let's say that I have a variable x, right? It's being stack allocated, it's an integer. And now let's say that I have a variable y, and y equals x. So I'm basically doing a copy from x into y, right? So I'm not moving any resources at this point in time. And I can print those values for x and y. Now, let's say that we have a, and a is going to be a pointer into something like a pointer of something that has been allocated on the heap, right? So we've allocated an integer on the heap, so a is pointing to that. I can print the contents of a, that's fine. Now let's say that I'm going to move a into b. So we say b equals a. When we move a pointer, in this case, we're effectively now transferring that ownership that a had of this heap allocated integer into b, right? And so now b owns it, right? And so when you go and try and display this, the same a, you're going to have an error, right? And Rust will throw that error for you statically, because it's actually tracking who owns what, all right? And that is example. All of the Rust examples come from some of their websites. Okay, now let's look at the concept of lifetimes. With lifetimes, what the compiler is trying to do is trying to check that a variable can be used throughout a particular lifetime, so a scope, right? And in this particular piece of code, let's say that I have variable I here. The lifetime of this I is going to be up to down here, right? So it's all of that scope. But let's say that I'm also going to have a few other variables, right? The scope for these ones is going to be lifetime, is going to be shorter, okay? Now, in this particular example, we have I. Now we're going to do a borrow 1, and we're going to have a shared borrow on I, right? So can we actually display the contents of borrow 1? Yes, that's fine, because the lifetime is up to there, and there's no conflict, right? Only one particular variable is making use of that borrow. Now we have another borrow, but notice I have it in a different scope. I'm doing mutable I. So in this case, I'm going to modify the contents of that particular pointer, and I'm adding 2 to it, I'm assigning 5 to it, and my scope ends here, okay? So all of that code is fine. Now, what happens if we modify the code a little bit and we remove some of these scopes that we had in the code? Now, let's say we had our borrow 3. we get mutable I, we change our borrow 3, so we change the content of it, we can print its value, and then we're going to have another borrow, and that's going to be pointing also to I. And in this particular case, we want to also display it, but in this particular case, the Rust compiler is going to throw an error to you because you cannot borrow I as is immutable because it has also been borrowed as mutable earlier on in the same lifetime, in the same scope of the program, right? So this is really cool because statically, you get to avoid a lot of these very common type of errors that you actually find in C and C++ programs, right? So very powerful abstractions. And with this abstraction, Rust is able to avoid having a lot of the most common type of memory safety type of errors that you see in other languages, right? Things like your buffer overflows, null pointer dereferences, double freeze, tail pointers, and so on, right? So that's cool, right? It does come a little bit of a price. You do need to get used to this new type system, and it can take a little bit of time, but once you fully are into it, people have a lot of fun with it. Now, Rust does have this ability to be able to have a way of escaping safe code, because you may want to be interoperating with a particular library that you've already written in C or whatever, right? And so for that purpose, they have this concept of unsafe that allows you to call foreign code, unsafe code, and so on, right? You can dereference even a raw pointer if you really want to. So to summarize, with Rust, we have a new security abstraction in terms of ownership lifetimes and borrows that allows you to be able to prevent a lot of the most common type of memory safety type of issues that you see in languages like C and C++. All of this is being done statically, which is great in terms of being able to determine the issues, like very quickly as you're developing the code. And it also doesn't affect performance, which means that the programs are going to run like pretty well, right? And so for people that care about performance and care about like memory safety, this is a new abstraction that really provides both of those worlds, right? You do, in some cases, need to make use of unsafe code because there's so much code written in the world that sometimes you need to interoperate with pieces of C code. Now, let us now look into,
Question regarding this unsafe code when the libraries of Rust are inside unsafe, but they still guarantee when you use them, they are safe to use. So we have these memory safety guarantees.
Right, so the compiler, so the question is like if you're writing unsafe code, do you still have like some of the memory safety guarantees?
No. So Rust, I think with Rust on libraries, you mean the standard library of Rust.
This one? Yeah, like Rust on library, right? Yeah.
So you write unsafe code within the functions, but Rust, when you use those functions, you still get these memory guarantees when memory safety guarantees, or how does it work?
Right, so what happens is that like the developer that writes the unsafe code needs to ensure that they're writing the code in such a way that they're not going to pollute the rest of the safe code, right? And of course, like for something like Rust on libraries, I mean, like the Rust developers are pretty good at doing this, so one wouldn't expect like issues in that space, right? What one needs to be more careful about is code that you've written, like yourself. Like let's say like I have an LDAP system and I want to integrate my LDAP system with some Rust code. In this case, you have 500,000 lines of C code that are already written in the LDAP system. And now you need to be more careful, right? Because there's a lot of code there that could potentially be breaking something, right? Nico, we were talking yesterday, looking at some potential ways of how to help developers like deal with this type of issues, you know, in the context of Valorant.
You want me to talk about it?
Yeah, sure.
One of the things we've been thinking about, there's a little bit, it's a very generous version. There are some things that are left, like that we're still working on around unsafe code that are pretty important, which is that getting the exact rules correct. There are some, the interaction of safe types, like the ampersand T, it must be immutable, and so on, for all pointers, is actually quite complicated, and we're still trying to figure out exactly what the rules ought to be there, although we have a pretty complete picture. And one of the things we would like to do is offer people the ability to run their tests with, I usually say Valorant, but really it could be any sort of instrumented execution, so that you can sort of check for undefined behavior in an aggressive way. So kind of like a sanitizer, if you're familiar with those. And this would let you really check that your actual code in production is obeying the rules, and helps, I think, if the rules are complicated, then at least you can test them. The thing I would say, basically that this one, that using Valorant and things like that, I mean, for example, when we run Firefox and so forth, we run that in Valorant. These are tools that can really scale up to large applications in practice. But you wouldn't be able to run it all the time in production.
Okay.
So in the examples you showed, the lifetime of objects was pretty small, just a few lines.
Oh, sure.
But I imagine that there are some objects that have much bigger lifetime that spans over complicated blocks of code. So here, garbage collection would then help a lot. How does it work on it, Ross?
So there's no garbage collection, right, at this point in time. So the compiler is really tracking everything just purely based on the lifetimes, right? And I have seen some errors that sometimes like they're hard to debug because you yourself are not quite sure, right? But once you really understand what's going on, it depends the size of your code and so on, then the compiler is actually telling you the truth. Right? Okay, let's move on to the next type of issues, injection errors. And in this category, we know that the unsafe abstraction has been the fact that we allow developers to do manual string concatenation, right? Like SQL injection errors, you saw them, right? Cross-site scripting errors, same type of thing. We're just doing like using strings, doing concatenations of many strings, and then we're assuming that the developers know at which point in the program they're going to do sanitization. Where are they going to check to determine that that string is a valid string for the type of operation that you're going to execute, right? This happens in a lot of different languages. You know, just about every language has this problem, right? And of course, in terms of safe abstractions, what has been made available here are two different models. We have like the link queue to SQL, which is one model that is purely only focusing on how to avoid SQL injections, right? So it's focusing on a subset of the problem. It solves that problem really well. And it's one of those examples where it's actually reaching that sweet spot, right? That is low cognitive load for the developers because they're just about writing the code almost in the same way as they used to. And it doesn't introduce a performance overhead, right? But there's another approach called Taint mode that was first introduced in the Perl language. It has been extended to the Ruby language. And with Taint mode, they're actually looking into more issues, like more types of injection attacks, and they're trying to prevent them, right? It does come at a certain performance overhead, right? Depending on your implementation, it may be down here or up here. It depends how much you want to track. And that is the trick with that one. So very briefly, I'm just going to mention about how to avoid SQL injections statically through an approach like link queue. Okay? So link queue is focusing like on SQL and how to deal with all of your data, right? And what they're doing is that they're trying to make use of kind of like the patterns, the way that people write code, to ensure that you're still passing the same code, but you're not doing the string concatenation yourself. What they're doing is that they're making use of SQL's prepared statement. And with the prepared statement, whenever there's a concatenation, because the concatenation never happens ahead of time, right? You're going to have like a certain part of your query that gets compiled, and then you're going to start passing some of the parameters, like for example, the employee ID, the username, the item text that we had, right? And all of these will actually go through the prepared statement. So by going through that prepared statement, the code underneath the hood is never going to have the string concatenation that most developers normally use in other languages, right? And so it prevents most of the issues. Is not 100% compatible with SQL, so like you cannot write all queries this way, but you can write most of the queries this way. So it's pretty good solution, right? Now, there's another approach, and this one is a dynamic approach.
Sorry, so the previous one was that we use some kind of smart constructor to fit the purposes.
Yes, so like underneath the hood, like the query plus everything that you're passing to that query is going to be like sanitized, so to say, right? By then checking like what is going to be sent, and then sending only things that make sense, right? And you're doing it all through like the prepare statement that SQL has, but yet like most languages don't expose like that functionality directly, right? Okay, so with the Perl language, they introduced a dynamic way of thinking about how do we prevent the injection type of errors. And they called it Taint mode. It was introduced a long time ago in 1989 in the Perl 3 version. And what they were actually trying to do was to automatically track any user controllable data, because anything that is user controllable is considered tainted, right? So you would take user controllable data that is now tainted, and the runtime system is going to track where is that data actually going to make it to. And they have a way of doing this, wait, let's look here. Yeah. And they have a way of doing this by having certain defaults, right? That anything that comes like from the command line arguments, anything that comes from an environment variable, and so on, by default, this is coming from the user, is tainted data, okay? So those are kind of like your entry points. But then when they're tracking the tainted data, what they're trying to do in the runtime system is to check that that data is not going to directly or indirectly reach commands that are going to invoke a subshell, because of course that could be bad, right? And also commands that are going to modify a file, a directory, or a process, right? Because again, you may be doing something pretty bad. But notice that they cannot do this for every single method. So for example, arguments to print or to syswrite, those are examples of data that they don't actually track, because it's a little bit hard to know which cases make sense, which cases may not make sense, right? And so that was a design decision. And notice that there's a few exceptions to the rule, to the general rule, right? So then if you look at some Perl code, you can see here like various different ways of how you can taint or not taint data, right? Like if you have an argument, well, by definition, argument is coming from the command line, that's tainted, right? Here, that argument, you're operating on that argument and you're going to assign it to HID. Well, now you've also made HID tainted by doing a direct transfer, right? So that's direct tainting. Anything like from standard input, that's also going to be tainted, right? You're going to have an open file, right? And then you're still going to be tainted because that's coming from a file. Environment variables, however, you're assigning a constant. That's an example of something that is not tainted because it's constant, right? And so on. Now, with the Perl Taint model, you actually have two different ways how you can execute the Taint model. You can let the system, Perl, the runtime system, do it automatically for you. And when it does it automatically, it's just going to check whether you have a different set user ID to the set group ID. And if that's the case, it would automatically run and warn you when anything tainted is reaching like one of those files or processes, anything that is dangerous, right? Or you could automate it manually with the -t command line option. And in that case, you're just telling the Perl interpreter, do this because maybe I've written like a server application and I actually want to be checking on that, right? Now, one thing that Perl does is that it starts untainted data automatically purely through regular expressions, right? So whenever you see like some piece of code where there's a regular expression, then the Perl interpreter is going to assume that you're sanitizing and hence you're untainting that particular data because that's why you're doing that particular check, right? So notice, again, this was a design decision, right? Like this may be correct or it may be incorrect, but that's the way that is done in this particular system. Now, a few years later, the Ruby language actually took on this concept and extended it. So rather than only having like the two levels that Perl has, 0 and 1, they actually went and extended it to level 2, which prohibits loading any program files from global writable locations. And even further, level 3, whereby any newly created object is considered tainted. And I mean, and all of you can imagine, you know, like level 3 makes it now like a little bit hard to start reasoning about like what your program's doing because it's much harder to do it at this level, right? Now, let's say that there was some piece of code, right? And in this particular code, like we have like a CGI form, we're going to get an expression. So assume someone has written like a calculator and all we want to do is arithmetic expressions. We're going to say, give me your expression, I'll execute your expression, right? Like 2 plus 3, 10 times 20, whatever, right? So we're trying to get that expression through here. And then we're going to eval, right? Like execute that particular expression, right? Of course, you can all see straight away, like not good idea, because we're not actually checking what we're going to be executing here in that expression. Someone could have written system remove star, and then we remove all of our files, right? So not a good idea, right? Now, what happens if we introduce like some of these safe levels, right? And let's say that we're using safe level 1, right? And here, we're going to have the same type of code, we get our expression, but we're actually checking, right, through a regular expression about certain type of characters that we don't want to have in our expression, and therefore, we untaint that particular expression. In Ruby, you as a developer actually have to explicitly tell the Ruby system that the data is now untainted. So it's kind of like you're saying, when I'm doing this type of comparison, I know that that's equivalent to untaint, and so now I've made this expression untainted, right? And so hence, if it's untainted, when you do the eval of that expression, the runtime system will let you do it, and it's going to execute that expression, right? So long as your regular expression is correct, then that is safe to execute, right? So that's pretty good, right? It prevents certain types of issues. But notice that in this very simple variation of the same code, actually it's just the same code with all of the comments, we do have a cross-site scripting type of attack that can happen. Right? Can anyone see it? Relates to one of the exceptions, right? Whenever there's exceptions, that's where you have to look for vulnerabilities. the same code. We're getting our expression. We're untainting it. We can evaluate it here. That's fine. But notice that we're going to do a print of this expression, right? So let's say that if you recall, initially I said there are some methods that actually don't get tracked in the runtime system. And print, syswrite are examples of those. So it means that I could pass, like whatever string, and when it reaches this print, it's going to just display that string, and I may actually end up with a cross-site scripting attack in this particular case. Right? Even though, we have sanitized, but we have sanitized for a different purpose, right? So to summarize, with Perl and Ruby, they're making use of this concept of taint mode to introduce a way of tracking injection attacks or prevent injection attacks through the runtime system. Right? Now, they're both doing it in similar ways. Ruby has more levels to track this type of data. And Ruby also allows you to programmatically taint and untaint specific methods. Right? So you have more control as to what you consider tainted, what you consider untainted. But overall, what you're seeing here is that there are still trade-offs that were made in terms of the implementation as to how much to track, what to track, because of course the more you track, and if you're tracking indirectly everything, that's even more complicated, right? And are you going to track like implicit flows as well, right? Even more complicated, then you're going to introduce more and more overhead in terms of performance runtime. Now, these trade-offs means that you can still have certain types of attacks happening in this model, like cross-site scripting. However, you can prevent a lot of other types of issues, right? And now let's look at the last category of errors, information leaks. And with information leaks, like the unsafe abstraction here is the fact that, again, we're manually having to track sensitive data, right? So you as a developer have to determine which is sensitive data and can I make it available somewhere else in the program, right? And so that's hard to do, of course. And with our safe abstractions, I'm going to talk about two different ways of doing this. Very briefly, I'm going to mention about policy annotations in GIF and Fabric, right? This is work, like, if you recall, like, there's no mainstream language that is actually using any of these abstractions. So this is work that is all in the academic literature, right? They've shown in the policy annotation work, like theoretically, you've been able to show that through tracking information flow, you're able to prevent a lot of these issues, right? It does come at a certain cognitive load. It wouldn't impose performance overhead over your solution if you do it statically, right? But that relies on pure static solution. There's another solution focusing on how to do it dynamically called policy agnostic programming. And with this solution, it does come like at a lower cognitive load, but it does come with a higher performance overhead. So everything is a trade-off. So very briefly, like the GIF model is a model for how to prevent information leaks and also injections in general. So it looks both at integrity and confidentiality, right? So it would be looking at like your tainted data, it would be looking at the equivalent of your information leaks. And here, GIF was actually a prototype that was developed many years ago. Like in the past decade, Andrew Myers has been working on this. They've extended the Java language, and they've extended it with various different types of annotations, right? And with these annotations, you're basically stating what type of policies you want to check in the system. And those policies are being tracked statically. So as you define various different arguments for different methods, you also need to start defining in annotations what are the policies that apply to those arguments, and then the compiler would actually start checking all of these for you automatically.
Annotations are just standard Java annotations?
Well, at the time when Andrew started, like the Java annotations didn't used to exist. So they were different, but if you were to implement it today, of course, you would just implement it with the Java annotations.
Okay, so this is kind of incompatible with regular Java source as it was done.
As it was done back then, yeah, because the functionality was not there, right? Yeah. Now I'm going to spend a little bit more time like talking about the dynamic approach on policy agnostic programming. With this approach, like key to it is the concept of faceted values. And what you want to do with faceted values is be able to keep track of your sensitive and your non-sensitive data along with the policy. All of it at the same time, right? And here, if we look at this example. Okay, so what you're doing with your faceted values is that imagine that you have a value, right? That value needs to be guarded by a policy, and you need to know what am I going to expose if this is sensitive. So if I'm a user that has access to sensitive data, I should be able to see the S value. But if I'm a user that doesn't have access to that sensitive data, I should be seeing the NS value, all right? And the idea here is that all of these policies actually get written outside of the code, just to simplify the implementation as well, right? And then the language runtime is the one that is going to enforce those policies for you. And they went a step further and they said, you know, in practice, a lot of the web applications are going to be backed by a database. So if we're tracking this information and we're not tracking it also when we cross and store data into the database, we're missing out on information. So they went ahead and introduced the faceted records idea into a database. And they did it like very simple in terms of their implementation. They just said it's the same concept as the faceted values, but we're doing it with records. So what we're going to do is that we're going to store 2 records for every single equivalent, like one conceptual record, right? And so if we have, for example, like a policy that in the true case is going to be like the first record, in the false case is going to be the second record. That equates to the sensitive data and the non-sensitive data, right? But they make use of a key just to track that both of these are actually part of the same conceptual record that they're trying to store into that database. And that's just like for prototyping purposes. This makes sense as an easy way to do it, right? And so what that allows you to do is that when you have like a full system, then the runtime system is actually keeping track of your faceted values in the code that you've written. It's also going to keep track of how it accesses the database, and it's going to return to you, you know, based on who you are, sensitive data or non-sensitive data, okay? And so they have like various different examples of applications that they've actually built using this model. And here you have an example of a social calendar application. Their actual implementation was like an extension to the Python language. And you can see that if you're going to have like this social calendar, right, and you're going to throw a surprise party, well, you don't want Bob himself to know that it's a surprise party, right? Whereas you want everyone else to know that there's a surprise party, everyone else that you're inviting to that party. So that's what you're storing here, right? Like a surprise party for people that need to know that. Bob himself, he should just only see there's a private event in the calendar, right? So that he doesn't know it's a surprise party. And then through the various different extensions, you can see here is how they're defining like the faceted value in terms of the policy. And they're saying that they're going to have a policy for the name, right? So based on name, whether it's Bob or someone else, we're going to go and restrict who can actually look at the event. So which record are you actually going to get back? And then based on that, it will tell you, okay, you get surprise party or you get private event. So you get the idea. Okay. So with this type of implementation, one of the really nice things is that for everything that deals with the database, they've actually automatically generated like all of the code for you. So you don't have to deal with the complexity of how to get correct like all of this code on the right-hand side. And they're making like like they're not changing like the SQL API, for example, that developers normally use. And then all of the faceted records get introduced by the system automatically. So that's pretty cool. It avoids some of that complexity of you now having to deal with, what do I do about these faceted records, and am I going to get it right? The runtime system generates that code for you. So to summarize, with this type of approach, in terms of their results, they have various different types of applications, where they've actually gone ahead and extended the applications. All of them are using like a database at the back. Of course, in terms of like amount of code, of policy code that has been removed, has been reduced overall because of the way of separating the code from the actual implementation. In terms of like auditing the code, it has made it much easier for people to audit the code. That's something that you do care about, like in systems like health record systems, where people manually have to audit all of this code, and it can take quite a bit of time. Now, in terms of performance, their current prototype, like for these 3 type of applications, it still has a performance overhead. Of course, it hasn't been fully optimized, right? So it is like, it has that potential of actually being like maybe a solution that could work well in practice, taking into account the fact that a lot of these applications are also going to be backed by a database. Okay? So all in all, with policy agnostic programming, we have like a new paradigm, right, that is trying to centralize all of your policy code outside of the actual application. And it introduces the concept of faceted values so that you can keep track of the policy, the sensitive and the non-sensitive value, all in one, and then the runtime system decides when each value should be shown to who. All right? So, with all of that, let's start now summarizing all of the information. With 53% of vulnerabilities over the 5 past recent years in the areas of buffer errors, information, injection attacks, and information leaks. And knowing that these 3 different areas are really in the realm of programming languages and programming language design, knowing that hardly any of our mainstream languages are using security abstractions in their languages, and none of them are actually providing abstractions for all of these common type of vulnerabilities. It is really important to start thinking about what is a secure language, and the definition that we're using is driven by data, right? We're saying that for the most common type of vulnerabilities, we ought to be thinking about how to avoid having those vulnerabilities by providing first-class security abstractions in the languages themselves. It is clear that today's mainstream languages do not provide the right support to our developers, otherwise we wouldn't have this many vulnerabilities. And it's also clear that none of our mainstream languages are actually secure languages. And in today's talk, I've mentioned like 6 different types of abstractions. I briefly also mentioned in passing, there's also information flow, so there's 7. I focused on 3 of them. Doesn't mean that the 3 that I focused on are like the only abstractions that one should be using. I was trying to give you an example of things that are not as well known or things that have the potential, and mixing like static solutions with dynamic solutions, because that is something that in the past, was not as common, whereas now we're at the stage where we can actually start thinking about dynamic solutions, not just only static solutions. Should we have a combination? Should we only have one side or the other, right? Wouldn't it be great if in the future there were a lot of other type of abstractions that were created, so that then we could start thinking about like, what is like the real abstraction that needs to exist to support our secure languages right here in the middle. And note that there's a lot of practical considerations that need to be taken into account. it's not like, you know, you can write your code in isolation and forget about like decades of work of everyone else written in other languages, right? Pragmatically, you still need to take into account the fact that you're going to have to interoperate through foreign function interface with some language, right? What do you do in that case, right? And some approaches that are being used, that are being researched at the moment in the community include multilingual compilers, multilingual virtual machines, and also linking types, right? And these are all at different levels of maturity, but these are concepts that could actually be used for this issue of interoperability. Another issue is also like if you're going to go for a dynamic solution, the complexity of modifying a VM is high. And there are other approaches that the research community has also been looking into, right? Can you do compilation that preserves security properties via translations that are fully abstract? And therefore, you're doing it kind of like outside of the VM rather than doing it inside of the VM, but you're still preserving the semantics. And that's the key important thing. And of course, like some people have said, what if we already had like solutions for all of those three common type of issues? Then are we done? Of course not, right? There's a lot of other type of vulnerabilities that are happening, right? I just focus on the three that were the most common type of issues. One of the large categories, another large category is this one that relates to permissions, privileges, and access control. If you look at the data in the National Vulnerability Database, that's the third most common type of issue. And I didn't include it as one of the focuses for programming languages because access control tends to be a solution to security. And what that really is telling us is that the implementation of the solution for a particular security issue, it actually has a bug, okay? So it's a different class type of error, right? Another common one that has risen in recent years is the cryptographic issues, right? Cryptographic issues has risen like quite a bit. And again, like what type of abstractions are we providing, right? Like writing correct cryptocode is very hard. There's issues about resource management. There's also like race conditions when you start looking at time and state. Of course, there are some languages that have started thinking about like some of these issues, like both Rust and Pony actually prevent data races issues, and this is like by design in their languages, right? Something that they care about is important for the domain where they're working on. Well, that's superb, right? Like there's some new abstractions that get introduced this way. And also, we all know that there are new paradigms that are being introduced as time goes by, right? We have microservices becoming more important. What does this actually mean in terms of vulnerabilities, right? Are we going to have like, are we going to be able to have security at the edge? Or are we going to be introducing new vulnerabilities at the edge, right? That's like another thing that we need to start thinking about. So with 18.5 million software developers worldwide, and this is a little bit old data from 2014, and notice 40% of them are actually hobbyists, but not necessarily going through a university degree, right? Like all of you, to get their accreditation. Security is no longer just for expert developers, right? And we cannot keep calm and carry on programming the way we've been doing it over the past 30 years. It's really time to introduce security abstractions into our language design. Thank you.
That means that you just have all race conditions solved, and of course, that's not really true. And functions? It would be much more.
So I actually didn't look in detail at the data race category because it's really small, actually, yeah. You know, percentage-wise, it was like, I think like in the order of 1.6%. So not very large, yeah. But I have the data. I can certainly, you know, like have a look through that.
So one question I have is with respect to your tainted, not tainted system. It's easy to say to consider that data coming outside from the environment is considered tainted, but for instance, there is a very subjective definition of what's actually tainted or should not be leaked or not. So how do you handle such a case? It's actually you must not absolutely edit another condition. Leak any email addresses or leak any password hashes.
Right, and there is where like policies actually come into play, right? Like, what is the policy for your application? What can we leak? What can't we leak, right? It needs to be defined. And that is normally like the hard thing. That sometimes, these policies are not well defined anywhere.
Plus there's the other issue, given that we have microservices, each one uses probably different language, hence a different runtime. How can you enforce policies across different runtimes?
Right. Yeah, so microservice is a good research topic, right? You can also have like other problems. For example, like one service may be storing some data into a database, and another service is later on going to read from that database, right? But now these two pieces of code are separate applications, right? And they may even be written in two different languages. If I'm only checking like one side, I don't know about the error on the other side, right? Yeah.
So what happens in this case?
Yeah. So that's like the same as a second order SQL injection, right? Like I could have a second order SQL injection in that case. But in order to be able to check for it, I actually need to be able to have a system where I can deal with all the code that is involved in that microservice, including all the languages that are being used for that microservice.